Okay, hello, welcome back to AMT 151 Basic Electricity. Please type in the chat if you can hear me. I want to make sure this thing is operating correctly before I get started with the slides. Okay, good. So today we're going to go through a few different subjects. First, resistance and resistivity. I'll review that a little bit from the previous lecture. I believe I loaded those slides, but we didn't go over it in lecture because I was having some internet issues on Monday. So I will pull up those slides and go through it a little bit. We'll also get into electrical power calculations, power in series and parallel, total resistance in parallel circuits, and capacitors. So here we go. Okay, so these are the slides from Monday that we went through. I was having some internet issues, so we only got so far. We talked about resistors and some of the makeup of resistors. We talked about the ratings, the color code bands, and how to read those. We went through an example of the color code bands and the ratings, and then I believe here is where I stopped because of the internet trouble. So you guys should have seen these slides. They were loaded on Monday. They're still on there now. It talked about variable resistors, what they're used for. Here's a little chart of some variable resistors, potentiometers, fixed wound, adjustable, and what their electric symbols are. Potentiometers, so you guys can read through that about potentiometers and rheostats used to vary current. Thermistors, okay, passive component, they operate on temperature. And photoconductive cells that operate on light sensitivity. And resistance and resistivity. So we did not get to this. I did not load these slides. I figured that was enough for Monday, so we'll go through it a little bit today. So factors that affect resistance. Number one, the material that's used. Number two, resistance is proportional to length. So the longer or shorter your wire is will depend on your resistance. Will make your resistance more or less. Resistance is inversely proportional to the cross-sectional area. So the area of your wire is inversely proportional to resistance, and also temperature affects resistance. So this is a fancy formula to figure out resistivity. This picture here on the left of the slide has your resistivity formula. And then this is an example, the picture on the right of a longer wire and a shorter wire, and you can see how the current changes in there and how the resistance changes in there. So the longer your wire, the more resistance. The shorter the wire, you'll have less resistance. That's all I really want you to know about resistivity. We're not going to get too heavy into resistivity calculations, but you do want to know how those factors affect your resistance. Most often you're going to have a chart depending on the wire that you're using. So this is a conversion table for copper wire. Gives you the American wire gauge number. Okay, so from quadruple zero to wire number 30, you have diameter in mils and your resistance for that wire. This is a video that explains a little bit about resistivity and the resistance of wire and how it differs.
In this video, we're going to talk about wire size, wire gauge, amperage, diameter, and other things related to this topic. Perhaps you've seen this abbreviation, AWG. This stands for American Wire Gauge, and it tells us the size of the wire and how much current it can safely handle. So the picture on the left represents a wire gauge of 10. The one on the right represents a wire gauge of 20. Now, what you need to understand is that the higher number corresponds to a smaller wire. A wire gauge of 10 has a diameter size of about 2.588 millimeters, whereas a wire with a gauge of 20 has a diameter of 0.812 millimeters. So as you can see, as the wire gauge increases in number, the diameter, or the size of the wire, decreases. So these two are inversely related. A wire gauge of 10 can handle a current of 30 amps, whereas a wire with a gauge of 20 can handle a current of 5 amps. So as the gauge number increases, the amount of current that it can handle decreases. Now the other thing we need to talk about is the resistance per unit length. The resistance per unit length of a wire with a size of 10 is 1 milliohm per foot, whereas the resistance per unit length for a wire with a size of 20 is 10 milliohms per foot. So as the wire gauge increases in value, the resistance per unit of length increases as well. So these are some things you want to keep in mind. So as the gauge number increases, the diameter size decreases, the amount of current that it can handle decreases, but the resistance increases. So here we have a table that lists the wire gauge, the resistance per unit length, the diameter size, and the ampacity, or the maximum current that the wire can handle at 60 degrees Celsius. Now the first thing that we can focus on is the relationship between the wire gauge and the resistance. As was mentioned before, as the wire gauge, as the number increases, the resistance per unit length increases. But notice that when it increases by 3, the resistance doubles. In this case, as it goes from 4 to 7, the resistance per unit length goes from 0.25 to 0.50. And as it goes from 17 to 20, we can see that the resistance doubles from 5 to 10. So every time the wire gauge increases by 3, the resistance per unit length increases by a factor of 2.
Build custom industrial machines and...
Now the second thing to notice is as the wire gauge increases by 10, the resistance increases by a factor of 10. So as we go from 20 to 30, the resistance increases from 10 to 100. So an increase of 10 in the wire gauge leads to an increase of a factor of 10 by the resistance. So those are some things that I caught looking at this table. Now the next thing that we can see in the table is that as the wire gauge increases from 0 to 40, we can see the diameter size decreasing progressively. And finally, as the gauge number increases, you can see that the ampacity, the amount of current that the wire can handle, decreases. So this just confirms what we talked about earlier in this video. It turns out that there's a formula that you could use to calculate the diameter size if you know the wire gauge number. And here it is. D sub n is equal to 0.127 millimeters times 92 raised to the 36 minus n over 39. So let's plug in 20. So n is going to be 20. So this is going to be 0.127 times 92 raised to the 36 minus 20 over 39. 36 minus 20 is 16, and 16 divided by 39, that is a long decimal number, so I'm going to leave it like this. Go ahead and type that into your calculator. So 0.127 times 92 raised to the 16 over 39. You should get this, 0.8118 millimeters. So that is the diameter size given a wire gauge of 20, which corresponds to the data that we see here in the table. So that's the formula that you could use if you want to calculate the diameter size in millimeters, if you know the gauge number. Now let me erase a few things. Let's work on a problem that we have on the top of the screen. A variable power source is connected to a 14 gauge wire that has a length of 9,000 feet. What is the maximum voltage that can be safely handled by this wire at 60 degrees Celsius? Let's begin with the picture. Let's say this is the wire. Let's call this points A and B. What is the maximum voltage that can be applied across this wire? Now this wire has a length of 9,000 feet. It's a very long wire. How can we determine the maximum voltage that can be applied? Well, we could use Ohm's law. V is equal to IR. The wire has a certain amount of resistance, and there's a maximum current that it can handle. So this is a 14 gauge wire. Using the table, we could see that the maximum current that it can handle at 60 degrees Celsius is 15 amps. So we have the maximum current. So we're going to replace I with 15 amps. Now the only thing that we're missing in order to calculate the voltage is the resistance of the wire. How can we determine that? Well, for a 14 gauge wire, we can determine the resistance per unit length, which is in milliohms per foot. And that's going to be 2.5. But let's convert that to ohms. So we have 2.5 milliohms per foot. And there's 1,000 milliohms per 1 ohm. So this is going to be 0.0025 ohms per foot. The resistance is going to be the resistance per unit length times the length of the wire, because those are going to cancel out. The resistance per unit length is 0.0025 ohms per foot. And so we're going to multiply that by 9,000 feet. So we can see the unit feet will cancel. And so it's 0.0025 times 9,000. And the resistance of this wire is going to be 22.5 ohms. So we can plug that into this formula. And that's going to give us the maximum voltage.
Big thanks to you guys at home.
So let's multiply 15 by 22.5. And that's going to give us a maximum voltage of 337.5 volts. Anything higher will exceed the maximum current rating of 15 amps for the 14 gauge wire. And so that's it for this video. So now you know the relationship between wire size, resistance per unit length, diameter size, and the maximum current that it can handle. So thanks again for watching, and don't forget to subscribe to this channel.
Hey, my name is Ben. Thanks for stopping by.
Okay, so that's a lot of information about wire resistivity. At this point in basic electricity, I don't believe you guys are going to be doing much with wire resistivity. I have to double check on your guys' testing questions. If there is, I don't see any wire resistivity equations. I think that the equation part might be in advanced electricity. So, but you guys do want to be aware that that equation exists and that there is a process for computing all of those things. And most of all, knowing that there are things that affect the resistivity of your wire. Okay, so that is everything from the lecture on Monday. Give me a second, let me get back to where I can see everything. Okay, here we go. Okay, so resistance and resistivity. We're going to talk about electrical power calculations now. So calculating electrical power from the scientific discipline of physics, the fundamental expression for power is P equals, this is what they call a script E over T, where capital P equals power measured in watts. The symbol for that is a capital W. And where script E equals energy measured in joules, capital J, and little t means time measured in seconds. So that is our equation for power. The unit measurement for power is the watt, capital W, refers to a rate of energy conversion of 1 joule over 1 second, or 1 joule per second. The number of joules consumed in 1 second is equal to the number of watts. So here's an example of that. Let's say we have 300 joules of energy that's consumed in 10 seconds. What would be the power in watts? So if we take our equation, we have our power, capital P, equals energy over time. That's our equation, right? So we have here our 300 joules. That's our energy that's being consumed in 10 seconds. In order to get to the power of watts, you would divide the two, calculate out the equation as it is, and that would give you the power would equal 30 watts. So another example, if a circuit has a known voltage of 24 volts and a resistance of 20 ohms, then the power in the circuit is. So this is another example of a power equation we're trying to calculate for power. So in this equation, we can say that power is equal to energy to the second power over our resistance, which our energy is our 24 volts to the second power over 20 ohms. This equation would give us a power rating of 28.8 watts. Okay, so you're going to see that there are multiple ways that you can use the power formula. So here is an example, Ohm's law and power formulas in a pie chart. So what this is telling you is, let's say you're looking for power, okay? So here we have the power, one of the power formulas, power equals energy times current. We also have power equals current squared times resistance. We also can find power by energy squared divided by resistance. Okay, so all of these equations are ways that you can find power given a certain set of circumstances. So if all you have is your energy, let's say we have that 300 joules, and then you have current, you can use those to calculate your power. That's what this pie chart is telling you. So that's how you read this. You have resistance. If you want to calculate your resistance, here's the formulas that, depending on what information you have, you can use these formulas to calculate your resistance, okay? So in this formula that I'm pointing at, let's say you're only given your power, which would be in watts, and your current, which would be in amps. So if that's the information you have, you can still find your resistance, and this is the formula you would use. But if you only have energy and you only have power in watts, then you would still be able to find your resistance even without current. Okay, so this is a good diagram to look at because all of these equations are going to give you the result you're looking for depending on the information that you're given. Another way to look at it here is we have Ohm's law and power formulas, and here is listing known values. So let's say you have current and resistance as a known value. Okay, so if you have a known value, your resistance and your current, even though you don't know your voltage and power, this is the formulas you would use to find them because you do have resistance and current. And that goes the same for all these others. Let's say you have voltage and current, okay? So if you want to find resistance, here's a formula where you could find your resistance. You would take voltage and divide it by your current, and that gives you resistance. And these are all variations of Ohm's law, right? Remember when we learned about Ohm's law at the very beginning of the semester? So all of these are variations using voltage, resistance, current, and power. And that's what Ohm's law is it's going to give you whatever you're looking for depending on the information that you have. Okay, so let's talk about power in series and parallel circuits. Remember, power being watts, okay? So power in series and parallel circuits. The law is that the total power dissipated in both a series and parallel circuit is equal to the sum of the power dissipated in each resistor in the circuit. So if you want to find total power, your formula here is going to just be, you're going to add the power of power 1, power 2, power 3, power 4, however many of those you have. If you want to find total power, it's just simple addition. It's going to be the sum of those. Power is additive in both types of circuits, parallel and series. Okay, we're going to go through some examples with resistance in parallel and series and the differences in those, but power is additive in both of those circuits. So resistance in parallel circuits. Resistors in parallel, let's say we want to find total resistance. Okay, so we've gone through before resistors in series, and we've found total resistance, or RT. Okay, so I have a couple of examples for you guys. And I think, yeah, I also have a video that has a couple more examples. So I have one here on your slide. So we have this diagram here, our resistors in parallel, okay? And it's a little hard to read, but still legible. I don't so much care. So we have our battery, but we don't have a voltage here because I don't so much care right now. We're just looking for total resistance. So that if we're trying to find total resistance, voltage and current doesn't really add into that equation. Remember, this is resistance in parallel circuits, okay? So in this diagram, in this image, we have a resistor connected in parallel that is a 5 ohm resistor. We have an 8 ohm resistor. We also have a 3 ohm resistor. Here is your formula for total resistance in parallel. Okay, and that's just for 3 resistors. I actually should add here, whoops. Well, you'll see in your textbook, and the formula is right now, because we only have 3 resistors, it's going to be 1 over the total resistance is equal to 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3. If we had more resistors, it would continue on and on and on. Okay? So I broke this down here for you as a mathematical calculation. If we want to find the total resistance of this parallel circuit, this is how that formula would look. We have 1 over our total resistance, RT. Our resistor 1 is 5 ohms. So we have 1 over 5 ohms. Resistor 2 is 8 ohms. So we have 1 plus 1 over 8 ohms. Resistor 3 is 3 ohms. So we have plus 1 over 3 ohms. We would convert that, we would just punch it into our calculator, and these are the numbers that we get, okay? So now our formula is 1 over total resistance equals 0.2 ohms plus 0.125 ohms plus 0. Repeating 3 ohms, okay? And then moving on, you guys can read the rest of this. I don't need to read it to you. It just continues to break down the mathematical problem. It's simple addition, multiplication that can be done on your calculator. But what a lot of people forget is they forget that total resistance is, in this equation, is 1 over RT. Okay? So when you get over here, we have our decimal, our result, our decimal number. Okay? And this is a repeating 3. I didn't really figure out how to put the little line over the 3, so I just put dot, dot, dot. So here we have 1 over our total resistance equals 0.6583 repeating ohms. Okay, that's what we got with all these calculations. Now, people forget this step right here and they think, oh, that's my total resistance. But you cannot leave it 1 over RT. We have to move that 1. We are looking for the total resistance, not 1 over the total resistance, okay? So what do we do if we want to get rid of that 1? Well, we're going to multiply by RT. So that cancels out the RT, the total resistance, and moves it over to the decimal side, right? So now we have 1 equals 0.65833 repeating ohms total resistance. Okay, but that's still not our final step because we need to get RT isolated on its own, just like simple algebra, right, you guys? So we're going to divide by 0.65833 repeating. So in the end, that gives us a resistance total of 1.519 ohms. So in that circuit, that is our total resistance. Okay? That's how it works in parallel circuits. Very different than in series circuits, okay? So just because, so in series, if these were in series circuits, we would just add them. Simple, easy peasy, right? But don't forget this step where you have to isolate the RT and you have to continue that equation out. Let's see, I also have another example on the board here, but I got to figure out how to get my camera. Um, video capture device. Okay, there I am. Oops. I'm not sure how well that's able to be seen. Hang on, I'm checking on my, I want to see how well you guys can see that, because if you can't see it, there's no point in me showing you guys the board here. Oh, okay, you guys can't see it. Let me see if I can move this closer. I guess I should have just put it on the slide, but I didn't. Good. Okay, so here we have another example. If you can read my handwriting, we have another parallel circuit, okay? I didn't write the battery or anything because it doesn't really matter right now. But we do have 3 resistors. So this here we have a resistor. Resistor 1 is 12 ohms. Resistor 2 is 20 ohms. Resistor 3 is 50 ohms. Okay, so I'm just going to go through these steps. I'm not going to use the calculator because you guys can calculate those things out. So we have our equation, right? If we want to find total resistance in a parallel circuit, we have our 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Resistor 1, 2, and 3, okay? So our resistor 1 is 12 ohms. We're going to put that over 1, or 1 over 12 ohms. Plus 1 over resistor 2 is 20 ohms. Plus 1 over resistor 3 is 50 ohms. So 1 over RT equals 1 over 12 ohms plus 1 over 20 ohms plus 1 over 50 ohms, okay? So remember, we're going to calculate these out to actual decimal points. And I am going to calculate them out. I'm going to use the calculator on my computer. Actually, I don't know if you guys can even see that. Okay, so we're going to do 1 divided by 12. That gives us 0.083 repeating. Okay, so we have 1 over resistance total equals 1 divided by 12 is 0.083 repeating, plus 1 divided by 20 0.05 plus 0.05 and 1 divided by 50 plus 0.02. Okay, so I'm not going to keep going because it's going to take too much time and there's a little more information that I want to get through. But you guys see where I'm going, okay? I'm just giving you another example. We have our formula. This is how we calculate that, okay? So we have all of this and we would have 1 over RT equals whatever this total is, okay? But that's not the end, right? What do we want to do next? Go ahead and type in the chat. I'm going to remove this, actually I'm going to leave it up there. Okay, does anybody know what we're going to do next? We have our decimal number here. So 1 over RT equals our decimal number that we've added with all 3 resistances. So what is that? Is that the total? 1 over RT equals whatever our decimal number addition is? Okay, yeah, I see. Multiply RT to the other side. That is what we want to do. So we have this, we'll call it X. I hope that doesn't confuse you guys. I guess I should just add it out. Somebody add that out for me. I gotta find my calculator again. $6.522. Okay, Hans Solo says it's 6.52. 6.522. Okay. That's not right. That's not right, is it? Anyway. Okay, so this isn't right, but what we would do is multiply by RT, okay? Multiply by RT. Multiply by RT, this cancels out. We have our number, 1 equals 6.522 total resistance, okay? And then we want to divide by our decimal number. Divide. And that would actually be our total resistance. Oh, I see. So the total came out to 6.522. Okay, so you guys can calculate that out, but big part is don't forget this step, okay? This step right here. You want to move that RT over because you can't leave it as 1 over RT, okay? So I'm going to, I think next I have this video. Let me remove my camera. Yes. I guess that didn't work. Now I don't know how to get rid of the camera. Okay, I think I figured it out. Yeah, I see the equation there that Trin brought up. I see Han Solo's, yeah, 6.522, okay, is the total. So whatever this decimal was, we multiplied the RT and then divided that by 1, and our total was 6.522, okay? So this is another video with some examples. And Thank you, Trin, for posting some of those numbers there. That came out, these three numbers, I'm pointing at the board, you guys can't even see me, came out to 0.1533, and then you want to, that would be over 1, so you would divide that, okay? So here are a few more examples, because we're going to be doing a lot of that.
The first day of class,
Parallel
filled with possibilities and
circuit
unknowns.
calculations.
That's why Check Study Pack empowers you with homework solutions and...
This video is all about how to solve DC circuits with parallel resistors. So consider the circuit shown below. Calculate the current flowing through each resistor. So let's call this resistor 1 and resistor 2. How can we determine how much current flows through the resistor? Well, we can use Ohm's law. V is equal to IR. So the voltage of the battery, which is the voltage across each resistor, that's going to equal the current flowing through the resistor times the resistor itself. So to calculate the current, it's going to be the voltage divided by that particular resistor. So we have 12 volts across this resistor, and if we divide it by 4 ohms, that's going to give us a current of 3 amps flowing through that resistor. So that's I1. Now to calculate I2, it's going to be the voltage of the battery divided by R2, which is 6 ohms. So the current flowing through this resistor is 2 amps. 12 divided by 6 is 2. Now how much current is delivered by the battery? Now keep in mind there's 2 amps of current flowing in this section of the wire. The current released by the battery is the sum of the currents flowing through each resistor. The current that flows through this segment has to be 5 amps. And it makes sense because at this junction, 2 went to the right and 3 amps went.
Okay, actually I changed my mind. I don't want to show you guys that video because it goes more into the entire calculation of the parallel circuits, and what I want to do is I want to talk about capacitors because that is a big portion of your quiz today. So we will get into resistance, current, and power of parallel circuits next lecture. So I'm going to move on to capacitors. There are no questions about the complete calculations for resistor current and power in parallel circuits on your quiz today, but there are questions about capacitors. So that is what I want to do. Oops. Thank you, Mr. Malone, for the information on how to add the overline. I will definitely try that. Okay, so that video was talking about DC circuits with parallel resistors, talking about the calculations for the entire circuit. There are no questions on your quiz regarding those calculations today. So what I do want to do, instead of having to redo your quiz, is I want to move on to capacitors. So capacitors. How do capacitors work? This is a picture of a capacitor. So capacitors are like a storage tank for electrical energy. They can smooth out electrical energy interruptions. Let's see. We have capacitors explained. This is actually a really good video, and I think that it will help you guys with your quiz. So we're going to watch that, and that will probably be it for lecture today.
I went to law school specifically to be a personal injury attorney.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at capacitors to learn how they work, where we use them, and why they're important. Remember, electricity is dangerous and can be fatal. You should be qualified and competent to carry out any electrical work. Do not touch the terminals of a capacitor as it can cause an electric shock. So what is a capacitor? A capacitor stores electric charge. It's a little bit like a battery, except it stores energy in a different way. It can't store as much energy as a battery, although it can charge and release its energy much faster. This is very useful, and that's why you'll find capacitors used in almost every circuit board. So how does a capacitor work? I want you to first think of a water pipe with water flowing through it. The water will continue to flow until we shut the valve. Then, no water can flow. However, if after the valve we first let the water flow into a tank, then the tank will store some of the water, but we will continue to get water flowing out of the pipe. Now when we close the valve, water will stop pouring into the tank, but we still get a steady supply of water out until the tank empties. Once the tank is filled again, we can open and close the valve as many times as we like. As long as we do not completely empty the tank, we will get an uninterrupted supply of water out of the end of the pipe. So we can use a water tank to store water and smooth out interruptions to the supply. In electrical circuits, the capacitor acts as the water tank and stores energy. It can release this to smooth out interruptions to the supply. If we turned a simple circuit on and off very fast without a capacitor, then the light will flash. But if we connect a capacitor into the circuit, then the light will remain on during the interruptions, at least for a short duration, because the capacitor is now discharging and powering the circuit. Inside a basic capacitor, we have two conductive metal plates, which are typically made from aluminium or aluminum, and these will be separated by dielectric insulating material such as ceramic. Dielectric means the material will polarize when in contact with an electric field, and we'll see what that means shortly. One side of the capacitor is connected to the positive side of the circuit, and the other side is connected to the negative. On the side of the capacitor, you will see a stripe and a symbol. This will indicate which side is the negative. If we were to connect a capacitor to a battery, the voltage will push the electrons from the negative terminal over to the capacitor. The electrons will build up on one plate of the capacitor, while the other plate in turn releases some electrons. The electrons can't pass through the capacitor because of the insulating material. Eventually, the capacitor is the same voltage as the battery and no more electrons will flow. There is now a build-up of electrons on one side. This means we have stored energy and we can release this when needed. Because there are more electrons on one side compared to the other, and electrons are negatively charged, this means we have one side which is negative and one side which is positive. So there is a difference in potential or a voltage difference between the two, and we can measure this with a multimeter. Voltage is like pressure. When we measure pressure, we're measuring the difference or potential difference between 2 points. If you imagine a pressurized water pipe, we can see the pressure using a pressure gauge. The pressure gauge is comparing two different points also, the pressure inside the pipe compared to the atmospheric pressure outside the pipe. When the tank is empty, the gauge reads 0 because the pressure inside the tank is now equal to the pressure outside the tank, so the gauge has nothing to compare against, both are the same pressure. The same with voltage, we're comparing the difference between 2 points. If we measure across a 1.5 volt battery, then we read a difference of 1.5 volts between each end. But if we measure the same end, then we read 0 because there's no difference and it's going to be the same. Coming back to the capacitor, we measure across and read a voltage difference between the two because of the buildup of electrons. We still get this reading even when we disconnect the battery. If you remember with magnets, opposites attract and pull towards each other. The same occurs with the buildup of negatively charged electrons. They are attracted to the positively charged particles of their atoms on the opposite plate. They can never reach each other because of the insulating material. This pull between the two sides is an electric field which holds electrons in place until another path is made. If we then place a small lamp into the circuit, a path now exists for the electrons to flow and reach the opposite side. So the electrons will flow through the lamp, powering it, and the electrons will reach the other side of the capacitor. This will only last a short duration though until the buildup of electrons equalizes on each side. Then the voltage is 0, so there is no pushing force and no electrons will flow. Once we connect the battery again, the capacitor will begin to charge. This allows us to interrupt the power supply and the capacitor will provide power during these interruptions. So where do we use capacitors? They look a little bit different, but they're easy to spot. In circuit boards, they tend to look something like this, and we see them represented in engineering drawings with symbols like these. We can also get larger capacitors, which are used, for example, on induction motors, ceiling fans, and air conditioning units. We can get even larger ones, which are used to correct poor power factor in large buildings. On the side of the capacitor, we will find two values. These are the capacitance and the voltage. We measure capacitance of the capacitor in the unit of farads, which we show with a capital F, although we will usually measure a capacitor in microfarads. With microfarads, we just have a symbol before this, which looks something like a letter U with a tail. The other value is our voltage, which we measure in volts with a capital V. On the capacitor, the voltage value is the maximum voltage which the capacitor can handle. We've covered voltage in detail in a separate video, do check that out, links down below. As I said, the capacitor is rated to handle a certain voltage. If we were to exceed this, then the capacitor will explode. Let's have a look at that in slow motion. Pretty cool. So why do we use capacitors? One of the most common applications of capacitors in large buildings is for power factor correction. When too many inductive loads are placed into a circuit, the current and the voltage waveforms will fall out of sync with each other, and the current will lag behind the voltage. We then use capacitor banks to counteract this and bring the two back into alignment. We've covered power factor before in great detail, do check that out, links down below. Another very common application is to smooth out peaks when converting AC to DC power. When we use a full bridge rectifier, the AC sine wave is flipped to make the negative cycle flow in a positive direction. This will trick the circuit into thinking it's getting direct current, but one of the problems with this method is the gaps in between the peaks. But as we saw earlier, we can use a capacitor to release energy into the circuit during these interruptions, and that will smooth the power supply out to look more like a DC supply. We can measure the capacitance and the stored voltage using a multimeter. Not all multimeters have the capacitance function, but I'll leave a link down below for the model which I personally use. You should be very careful with capacitors, as we now know they store energy and can hold high voltage values for a long time even when disconnected from a circuit. To check the voltage, we switch to DC voltage on our meter, and then we connect the red wire to the positive side of the capacitor and the black wire to the negative side. If we get a reading of several volts or more, then we should discharge that by safely connecting the terminals to a resistor and continue to read the voltage. We want to make sure that it's reduced down into the millivolts range before handling it, else we might get a shock. To measure the capacitance, we simply switch the meter to the capacitor function. We connect the red wire to the positive side and the black wire to the negative side. After a short delay, the meter will give us a reading. We will probably get a reading close to the stated value, but not exact. For example, this one is rated at 1000 microfarads, but when we read it, we get a measurement of around 946. This one is rated at 33 microfarads, but when we measure it, we get around 36. Okay guys, that's it for this video, but to continue your learning, then check out one of the videos on screen now, and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, Instagram, and of course, theengineeringmindset.com.
Okay, so that's it for this lecture. Make sure you guys take the quiz before midnight tonight, okay? And Mr. Kimball, we'll see you in lab. Anybody have any questions? If you do, go ahead and type in the chat, or if there's a slide that you want to see, you can type in the chat. I'll wait just a couple minutes. If not, I'll see you guys Monday for lecture, and Mr. Kimball will see you in lab.